computation of a Fourier series of a function simplifies a bit if a function of f of x is either even or odd. In that case, either the a n are 0 if f is odd, or the b n are 0 if f is even, so this saves us half of the work. But why is this? And what again did it exactly mean that the function is even or odd? That is what you will see in this video. We will first review the notion of even and odd functions, and after that we will see how this helps us to simplify the equations for our Fourier coefficients. So what do we mean with even? If you have x and minus x both in the domain, then for all those x's we need to have f of x equals f of minus x. They have to be at the same height. And the function is odd if for the all x's and minus x's in our domain, f of x equals minus f of x. So it's on the other side of the x-axis. So let's make a picture to see how this looks. So for an even function, so say for positive x's our function looks something like this. Then how should our function then look for negative x values? So if we have a function value x and f of x here, then f of minus x should be the same as f of x, so at the same height, so it should go somewhere over here. And take some other value of x, say over there, then our f of x is somewhere over here. Then f of minus x should be the same height, so go somewhere over here. And the total picture, you see the pattern in writing, looks something like this. So your total function is symmetric in the y-axis. So you can recognize from the picture already whether your function is even. Now what about odd functions? You can do something similar. Say our function looks like this for some positive values of x. Now we take again some value of x here. We have f of x then over there. And f of minus x should be then minus f of x. So should go somewhere over here. And for some other value of x, we have our f of x here. And the f at minus x should then be minus this f of x. So it should go somewhere over there. So the total figure, recognize the pattern hopefully, looks something like this. So it is, you can recognize this from the picture because it's symmetric by mirroring through the origin. Now let's take a look at some typical examples. Like a typical even function is say 1 or x squared. Take a look at f2 for example. If you take a look at f of minus x, you get minus x squared equals x squared. So the f2 of minus x equals the f2 of x, so even. Typical odd functions are g1 equals x and g2 are x cubed. Take for example the g2 of minus x. Then you get minus x cubed, but minus x cubed equals minus x cubed equals minus g2. So that's an odd function. And functions are neither, for example, e to the power x or 1 plus x. Take for example the f of minus x, then you get e to the power minus x. But e to the power minus x is in general not equal to e to the power x. And e to the power minus x is also not equal to minus e to the power x. So f of x is neither even nor odd. Now you recognize already, like here we have x to the power 0, x to the power 2, or x to the power 4, or x to the power 6. So x to some even power is an even function. And here we have x to the power 1, x to the power 3, x to the power 5. X to some odd power is an odd function, hence the name. Now we have some useful properties. You probably saw them already in some more basic calculus course, so I just repeat them over here. So if you have a number of even functions, and if you then take linear combinations, you still have an even function. Or if you have odd functions and you take some linear combinations, you still have an odd function. And if you have even functions f1 and f2, or odd functions g1 and g2, product of even functions remains even, product of odd functions is even as well, and product of even times odd becomes an odd function. Again, you can prove this quite easily. Not going to do it now. Hopefully you've seen this in a more basic calculus course. Because what do we need from all of this? We need this for our Fourier coefficients, so we need this for integration. So let us focus on the integration. So if we integrate some general function from minus L to L, then we can split up the integral in two parts, minus L to 0 and 0 to L. Then we can use the substitution rule for the first integral, setting x equals minus u. We get f of minus u, d minus u, x equals minus u, so x equals minus L becomes u equals L and 0 remains 0. And we just leave the second integral as it is. And we then flip the integration order in the first integral, which costs us this sign over here. And then rename the integration variable u to x. And we get an integral from 0 to L of f of minus x plus f of x, which we left as it was. And then we notice something useful. First of all, if f of x is odd, then f of minus x equals minus f of x, and the integral cancels out. So if you have an integral from minus L to L and our function is odd, the integral will always be 0. Now, if our function is even, then f of minus x equals f of x, and we also simplify a bit, then we have here the f of x as well, and we get twice the integral from 0 to L of f of x. So it mainly helps us if f of x is odd. Now let us apply this to our Fourier coefficients. Now the general formulas are given here for the an and the bn for some general f of x, but now something special happens if f of x is either even or odd. Let us first take a look at the case f of x is even. Well, if f of x is even here, then cosines are even. We have the product of even is even. So the an equals the integral from minus L to L of some even function, but that is twice the integral from 0 to L of the same function. Okay, that does not help that much. However, if f of x is odd, then odd times even from the cosines gives us an odd function. Integral from minus L to L of an odd function is 0, so then the an's are 0. Now let's take a look at the bn's. If f of x is even and the signs are odd, then if f of x is even, we have even times odd gives us an odd function, so then the integral becomes 0. And if f of x is odd, then we get odd times odd is an even function, and the integral becomes twice the original integral. So this helps us to compute our Fourier coefficients, because if our f of x is even, we only need to compute the an, and if f of x is odd, we only need to compute the bn.